Okay, so hello, welcome to another one of my video log recording sessions where I talk about genetic algorithms and how to improve such algorithms, I guess. Where I study about genetic algorithms, let's just say, from the very basic stuff and hopefully on to more advanced topics. Stuff. I love saying the word stuff. Okay. So, the date is 2025, April 5th, and I need to cough. And today I will be covering again 7 notebooks. Hold on. Yeah, 7 notebooks, which are General Genetic Algorithm Grid Search Normal 2, General Genetic Algorithm Grid Search Log Normal 2, and Uniform, Exponential, von Mises, Pareto, and Weibull. Okay, so those are the 7 notebooks, but this is like, well, these notebook files are the third versions of themselves, and the general purpose of these notebooks were to assess the genetic algorithms and evolution, where the items and the genes and the corresponding utility and constraint values were generated from one given distribution, one specific given distribution. Well, specific and given, they're the same. So from one given distribution per iteration, iteration as in from generation 1 to the last generation, and in order to determine when dips appear and disappear in terms of maximum constraint percentage. So today, to explain or visualize what this means, I'm going to use the Paint again, Microsoft Paint again. So, for example, if the total number of generations is 500, and I were to do this 5 times, so per and call this one iteration, so these would be 5 iterations of generation, 5 iterations of evolution over 5 iterations of evolution over 500 generations. Okay, now per iteration, the items, the items will be generated from item 1 to item n, and the corresponding values, as in the utility values, utility value 1, values 1 to all the way to n, and constraint values all the way to n. So that will be done per iteration, and when the 500 generations is over, we go on to the next iteration, and then we generate again. So these two sets of 3 three kinds of values are not the same. Granted, they will be generated from the same distribution per notebook. For example, in this notebook, they will all be generated from a normal distribution, sampled from a normal distribution separately. So these are also different values, but these values are not these values. They can be similar, but they're not the same. Sorry, I had to cough again. So again, given a distribution, these will be sampled every time. And once this iteration is over, we do it another time. But again, from the same distribution. So these two coming from the same distribution. These two coming from the same distribution. These two coming from the same distribution. But every iteration will be a new set of items, utility values, and constraint values from one given distribution. For example, a log normal distribution, or an exponential distribution, or something like that. Or what was it? The other one. Oh yeah, uniform and exponential, uniform, von Mises, Pareto, and Weibull. So 7 distributions, hence 7 notebooks, 7 NBs. So with that out of the way, we'll just well, because since this is the third time I am covering, well, this series of notebooks, I'll just jump straight to the results. As soon as I am done with the maybe hyperparameters, or maybe some changes. Yeah. So hyperparameters again, number of items 10, which means the length of the genome or the entity, and apart from that, nothing has actually been changed. Well, we'll get to that. Nothing much has been changed, and we create the void genes. We create the void genes, store the values, create a list of max constraint percentage lists. I really should stop coughing. And this is how it goes. Per maximum constraint percentage, we do it for 5 times, and evolve it for over 500 generations. However, per iteration, we generate the items and the values, 2 sets of values, and then calculate the total utility and the total constraint. Total constraint, and on we go. And what happens here is, what happens at the end is what, well, these plots, these charts and plots, will have a histogram, will have an average dip plot, average dip percentage plot, and the generation against summed utility plots in terms of heads or top entities, and the top 10% for the top 10% entities. These we've seen many times by now, but the last one, the peak plateau plot, will show us how the peaks and the plateaus progress over the maximum constraint percentage, and eventually it'll just show us how they diverge. For example, towards the end, this is what you get. So these are, this is a new plot that I have introduced in order to visualize things, and ultimately for me to understand things better. So yeah, so when we have 10 items for the from the normal distribution, this is the entity distribution, somewhat of a normal distribution. Again, central limit theorem. And this is the average dip plot, usual as expected. This is the average dip percentage plot, usual as expected, because we only have 10 items. And the average and the generation against summed utility plots, where the x-axis is the generation and the y-axis is the summed utility values. And these are the plots for the heads. 5. Oh, one thing to note in this notebook and in some of the others as well, is that although the maximum ever and the total utility are in black and red, and the total utility was usually always at the top, but in this series of notebooks that is not the case, because the total utility changes per iteration with every iteration. So this red dash dotted line is the total sum of utility values of the last iteration. And there will be times when the maximum ever is higher than the total sum utility values of the last iteration, which doesn't make sense, which would not have made sense in the previous series of notebooks. But I just had to clear that. So these are the plots for the heads, top entities. So here the thing we have to look out for is the black line, when the plot hits the black line. We go down and we still haven't hit the black dash dotted line yet. We see things happening. Again, the plots are very flat because we only have 10 items. 95, yeah, at 95 we hit the black dash dotted line, maybe at 100 as well. So 90, 95 and 100, we look at those. These are the plots for the top 10%. Now we see some oscillations and some plateaus and peaks. Average dip percentage 8.35 at 90%. Average dip percentage 9.19 at 95. Average dip percentage 9.41 at 100. Yeah, and the peak plateau plot. There were absolutely no dips until about, what is that, 10, 11, and then starting from 12.0 we started getting some dips, well, slight dips, and then the dips got larger towards the end, again because we're dealing with only 10 items. So what about 40 items? This is the entity distribution, very pretty, a pretty normal distribution. Average dip plot, so usual. Average dip percentage plot, usual. Again, this is because of the entire evolution scheme where no procreation happens as the maximum constraint percentage goes up, because no entities are being struck out. I've said that multiple times. However, I still find that very hard to phrase. It's very wordy. It's a mouthful. So the maximum average dip percentage was 10%. We'll have a look at the series of plots. Maximum constraint, we'll look out for when the plots hit the black line. $75 no, $80 no, $85 no, $90 no, $95 we have, and $100 we have. Cool. Now, again, looking at 95, 20, 25, 30, 35, 40, 45, 50, 60, 65. Still not much of a dip. A slight dip. 75, and now that's a dip. 7.13. 10.1%. Yes. 85, 90, 95. So wait, when did yeah, at 95, this is odd. At 95 we hit the maximum ever, but the dip got smaller. Okay. Looking at the peak plateau plots. Yeah. Kind of expected. What we just saw could have been just an anomaly. Okay. 100 items. Entity distribution. Normal. Well, as expected. Average dip percentage plot, as expected. Average dip percentage 0.08, so that's 8%, right? Yep, I think so. Heads, when do we hit the black line? Black line. I should speed this up, but anyway, this is the first notebook, so at 85 we kind of hit, I think, the maximum ever. At 90 we do, I think. 95 we don't. 100 we do. That's cool. So let's have a look at those from the very back. 35, slight dips happening, and now that's a dip. 75, 90, 95. Okay. So that's odd. At about 70, we had the peaks. However, the maximum ever did not occur at 70. Or did it? Did I miss it? No, I didn't. Okay. So this could be, it could be said that when the maximum constraint percentage was at 70%, there were more entities with higher sum utility values, and therefore the score for the top 10% increased and peaked. But when this was happening, the maximum ever value did not happen. So when it actually did happen at 90 and 95, was it? And maybe at 100 too. These were just, luck, because the plateau just stayed the same. Yeah. Okay. So next one. I'll be quick. Next one, we're using the log normal distribution. So we're sampling it from log normal, all these values. Entity distribution, kind of. Again, in this series of notebooks, the entity distribution plots will look less normal, because the items generated and used for the evolution are different items, and therefore we're not actually sampling from one identical bigger sample, but not, so and as a result, the central limit theorem tends to manifest itself a bit less. So 10 items, entity distribution, average dip plot, quite usual. Entity average dip percentage plot is also usual. Generation to sum the utility plots. When do we hit the black line? See, this is what I meant. The total utility should always be higher than the maximum ever if the items were fixed, but they're not fixed this time, so that's why this is happening. So watch out for when the plots on the lines hit the black line. Not there yet, not there yet. There we go, at 70. Okay. So at 70, we have to look at when maximum constraint percentage is at 70%. We go way down. 70. Where is 70? There we go. Okay, we do have some peaks now. I wonder why this happened, and then it never went that high up. But I should add that this series of notebooks is they're not that accurate. And when we try to compare these plots one to one, because they're all different items, and it wouldn't be fair to say that, oh, this performed better than this. This series of notebooks is just for the purpose of seeing the shapes of these plots, curves, and the slopes. Peak plateau plot. So this is quite unusual, as shown also here as well. But this plot is also unusual, but again, due to the fact that the items are being sampled from a log normal distribution per iteration, and that's what causes the abnormality in values. So if I were to do this more accurately, I would have to do everything 5 times. Sample this, run it 5 times, sample this, run it 5 times, sample this 5 times, sample this 5 times, and 5 times. Because right now this is one iteration. I need 5 iterations of each, which would have, of course, fivefold the total runtime. Because all these notebooks as well took how many minutes? Yeah, about 100 minutes per notebook. So I may need to find a way to scale probably horizontally by using AWS or something, or just Google Colab, buy more compute power on Google Colab. I think that's also a viable option, would also save time. So heads for 40 items, entity distribution for 40 items, again looking quite normal, but less normal than before. Average dip plot, usual. Average dip percentage plot, usual. Here are the some utility plots. When do we hit the black line? $80, $85 we do. Wow. Okay. 90 we almost did. 95 we didn't. 100 we didn't. So I guess what happened here, and also when we had 10 items, is that when the maximum constraint percentage was at 85, something happened and caused this. Some mutation happened, some mutations happened, and then some of the top entities got to procreate, and that led to this and this, the maximum ever value. Yeah. However, when it was at 90 and at 95 and 100, because nothing's getting struck out, we just stay here. Everything's just kind of mediocre or medium. Peak percentage plot, again very unusual compared to the one we got last time. Let me just bring that up. I think from log normal. No, wait. I didn't have this plot in my previous videos. I may need to rerun them. Oh my god. That's a lot of work. Okay. 100 items. Entity distribution, average dip plot, same, heads. 50%, wow, no, we got lucky there. 55, no, we didn't get lucky. 60, not so much. 65, no. 70, no. 75, no. 80, no. 85, no. 90, 95, no. 100. When did the maximum ever happen? Oh, here, at 50. Okay. And peak plateau plot, very unusual. Again, due to the fact that we're sampling each time, per iteration. So uniform distribution, same thing, but everything sampled from a uniform distribution. 10 items. Yep. Average dip plot, same. Heads. we hit it at 100%. So, again, very usual. Let's see what happens at 100 for the top 10% entities. So, kind of different, this peak plateau plot, but yeah. But I guess the difference is due to that fact, the everything being sampled per iteration. So 40 items. Entity distribution, same. Average dip plot, same. Average dip percentage plot, same. Heads, same. The maximum ever happened at 70, 75, 80. At 70 it did. Let's see what happened at 70. And the peak plateau plot, yeah, kind of expected, kind of similar, I think. No, not that similar. I mean, similar to the ones we had before. I know I said I didn't have these plots previously, but from what I remember, this is quite similar. 100 items. Okay, entity distribution. Average dip plot, same. Average dip percentage plot, same. Heads. Well, this is unusual. At 75%. Something happened there at 75. Okay, so this is kind of similar to this. Exponential, 10 items. Let's have a look at the peak plateau. Wow, this is quite different. When we had this, it actually went down. But again, I think this is because of the fact that we sampled per iteration. Top 10%. At 50, we hit it. Nope. Heads. Okay. Okay, we can just move on to 40 items. Entity distribution, normal, average dip percentage, normal, average dip plot, percentage plot, all the same. Heads. $60? No. 65, 70, 75, 80, 85, 90, 95, 100. So let's have a look at 60%. 60%. 60%. 70%. 75%. 80%. 85%. Well, so by now I think I can just safely assume that dips happen as far as the way we evolve, or the way I evolve things are, is concerned, and stays the same. Dips happen at around when maximum constraint percentage is 70%. Peak plateau plot. Okay. (100) items. Entity distribution, same. Average dip plot, same. Average dip percentage plot, same. Average dip percent summed utility plot. At 60%, 70, 75, 80, 85, 90, 95. But the maximum ever is, there is a chance that the maximum ever value is not actually the maximum ever value in relative terms. As in, in terms of how relative a value is to its own total constraint value, total sum of constraint value of its own within that iteration. 60, where is it? Is it here? No. Where is it? Where is it? Oh, is it 65? Low? 80, 100, 90, 95, 70. Yeah, so when we talk about that, this value hit the maximum ever, but this could actually be lower in relative terms when compared to, for example, this. Just because the sampled items and their values are different. So I just have to keep that in mind. But I'm here for this, aren't I? So dips happened. Yep. When did the dips happen? At around, again, 70. Mostly at 70. Vermeer. Entity distribution, average dip plot, average dip percentage plot, summed utility plots, peak plateau, yeah, same. Entity distribution for 40 items, entity distribution, average dip plot, average dip percentage plot, yeah, heads, tops, okay, peak plateau, again around 70, but these are really fat dips. Yeah, because they're all 16 at 16%, the dips. Okay. How big were the dips? Like, I want to see them. Yeah, these are quite big. So I think it's better, now that I know that they will behave somewhat in similar manners, I think it's better to just fix the items. Yeah, so fix the items for better comparison in my next experiments. So 100 items, because if I don't do that, it's hard to compare. It's hard to draw a accurate comparison from this. They're all different lines. So entity distribution when we have 100 items, same. Summed utility plots, yeah, I think that's what I should call them. Okay. Top 10%. Yeah, about the same. Peak plateau plot. Okay. Pareto. Let's just be quick. 10 items. Entity distribution. Okay, same. Average dip plot, same. The percentage plot, same. Heads. Yep. As usual. For 40 items. Kind of usual. Yeah, at around 70 we have the dips. 100 items, we have the dips. Yep. Heads. Maximum ever happens at around 85, 90, 95. At 100. Wow. But again, these are not the same values. These are recorded as maximum ever because the values used here, sampled and used here, could have been just bigger to start with. So not that accurate. Variable distribution, 10 items, peak plateau plot, yeah, about the same. Entity distribution, about the same. Average dip percentage plot, same. Heads, let's just skip that, since we now know that they're not actually that accurate. Average entity distribution when we have 40 items. Average dip plot, average dip percentage plot. Heads, no, we can skip that. Peak plateau plot, about the same shape. And plateaus happening at around 70. 100 items, plateaus happening mostly at around 60 to 80, so 70. And let's just see the peaks and plateaus. Yep, happening, and not happening. Okay. So, sorry, wait. So, my conclusion in this video is that number one, it's not such a good idea to sample the items and their values per iteration, because then the comparisons are not that accurate. And since I have seen that their behaviors are mostly the same, almost the same, when we actually have the items and their values fixed, I should just stick to fixing the items, not sampling them every time per iteration. And secondly, the peak plateau plot, the PPP, I think this is a very useful plot. And third, peaks happen. As far as the way I'm evolving the entities is concerned, and it stays the same. That is when I don't strike out entities. That is when I don't strike entities because none of them actually went above the threshold and therefore never introduced new entities. The innovation stops because there are no procreations amongst the top entities, and the overall performance or the evolution stops quite quickly, and there will be no nothing there are no breakthroughs, rather. I think that's the right way to say it. They just stay there, stagnant, when I'm sure that these values could have been way up there had I made a better evolution scheme. So that's about it. Next time, what should I do? How should I change this? So fix the items. Fix items and values. Go through all the max constraint percentages, right? Use the peak plateau. It's so hard to spell plateau. EAU plot. Well, not only this plot, but make sure to add this. Make sure to add this on top of all the other plots. What else? And when I'm done with that, done with this series, the series after that, I would have to introduce new entities, even when none are struck out. Yeah, I think that's it. I think this is the gist of it. Okay. Oh yeah, and also test things when the distribution is left skewed. I need to add this too. But I'm kind of certain that this will also behave the same. Okay, well, thanks for watching. See you next time. Peace.